Hello and welcome to this short video on the good and the bad of underwater acoustic communications. So whenever I tell people about the excellent properties of the underwater ocean medium in carrying faraway sounds, they immediately ask me if the ocean can indeed be used to carry the internet, um, carry videos, that kind of stuff. So this video is a short explanation of why that's not such a good idea. But then there are some other redeeming qualities of the underwater acoustic communications medium. So I thought I would title this as the good and the bad of underwater acoustic communications. Okay, so the good, in short, is that the underwater ocean medium has something like an acoustic waveguide that carries sounds to far ranges. I will show you how the waveguide works. I'll give you a conceptual picture of it, and I'll also explain why it's a bad idea to think of carrying broadband internet in the ocean without wires. Uh, the reasons being the short bandwidth, um, there is multipath, and there is also the effect of oceanographic fluctuations. So first, the good. Okay, so um, in in the deep ocean, let's start with the deep ocean. You have the sound speed profile as a function of depth. So you go from top to bottom in depth. What happens is the sound speed profile, because of the way the temperature gradients, the salinity gradients, and the effect of pressure all work together in the temperate ocean, for example, you'd find that the sound speed profile um, decreases up to values of 1480 meters per second, and then it increases further in depth. Okay, so you have this. Okay, and the lowest values are somewhere around approximately 1480 meters per second, and these can be the top and the bottom. It can be 1520 meters per second, 1560 meters per second. So that's the typical values of the sound speed profile that exists. Okay, now the sound speed profile can look different depending on which part of the world that you're in. If you were in the Arctic, the sound speed profile would look something like this. So I'm going to call this the sound speed profile. So this is SSP in Arctic. Okay, now if you were, say, in the tropical ocean, you'll still get this kind of a sound speed profile that you see on the left, except that the minimum would come maybe a little deeper. Okay, so this is a tropical sound speed profile. All right, now what does this do to propagation of sound? Okay, so now because of this, if say I put, say, a source at somewhere around the sound speed minimum, then so propagation in the deep ocean, right? So acoustic propagation in the deep ocean. Okay, so if we have a sound speed profile like this, I have this, right? And say I put, say, the source. For simplicity's sake, I'm just going to denote the source by um, just a point, okay, just a dot. Okay, I'm going to abstract out all the complicated details of how an acoustic source works, and I'm going to show it just as a dot. Okay, so now because of this, what happens is, say the source shoots sound in different directions. What's going to happen is the sound that goes up is going to get curved back down, that comes back down and gets again curved back up, and so on. The sound that gets shot in this direction, it's going to come back like this, it's going to do this, it's going to do this, and so on. And the sound that gets sent in a horizontal direction, it will propagate horizontally. If it's at a smaller angle, then it does this. Okay, so what happens is, with this, the sound paths that you see, right, they don't touch the bottom. Okay, and this is the top, right? So they don't touch the top or the bottom. Okay, if they were to touch the bottom, they would get attenuated and they don't travel that much far. So that would be something like this, bloop, gone. Okay, something like this, that's gone. Okay, but then there are other rays which get trapped around the sound speed minimum and they get propagated out to far ranges. Okay, now these would suffer only cylindrical spreading, okay, and no losses due to interaction with the bottom. Okay, so this is great for propagation because sound would get carried without any attenuation due to interaction with the bottom and only cylindrical spreading. Okay, now that's the first picture. So that's your acoustic waveguide. So because this carries sounds from far. Okay, now what else is present in the waveguide? Now there is also the effect of attenuation due to viscosity. Okay, so there is volumetric absorption, okay, which puts a limitation on how far these sounds can go. Okay, now I'm going to call this volumetric absorption. Okay, effect is high for increase in frequency. All right. Okay. How bad is it? Okay. So what do I mean by high frequency? Okay. If your sound were as low as 50 hertz, 25 hertz, you would get only a very small fraction of a dB per kilometer. Okay, but if you go into high frequencies, say something like in the high kilohertz, like 500 kilohertz or even up to 1 megahertz, then if you're going up to 1 megahertz, your sound will propagate only a meter, and you just get noise, and that's it. Okay, so the usable bandwidth, okay, right, is something like say some 10 hertz or so. Lower than that, you can build a source. It's fine. Yeah, there are low frequency sources too, and then you probably go up to like 500 kilohertz or so. Okay, so the usable bandwidth is only very low. Okay, now what does this have for carrying the internet? Okay, now we look at Shannon's theorem for channel capacity. This comes in communication theory, this comes in information theory. So the channel capacity, right, in terms of in the units of number of bits, the maximum number of bits per second that can be transmitted across a communication link is given by the bandwidth BW times log to the base 2 1 plus signal power divided by noise power. Okay, so this is the SNR, but SNR in linear scale. Okay, now this one is the bandwidth in hertz. Okay, so that is what it is. Okay, so now if you look at this equation, you'll see that the bandwidth has a much bigger effect on the number of bits that you can push through the channel than the signal to noise ratio that is there. Okay, so we care much for bandwidth. Okay, all right. So now any source that you intend to use for communications, right, has a Q factor. Now what is this Q factor? Now the Q factor is the bandwidth divided by the center frequency. Okay, now if you want a higher bandwidth for your source, okay, now you'll have to you need a higher Q. Okay, now for the same value of Q, right, you could go to a higher value of center frequency. Okay, so I could write bandwidth is FC times Q. So if you fix Q, you have to go higher in frequency. Okay, now the Q factor, turns out, is also inversely proportional to the efficiency of your source. The efficiency in converting your electrical energy into acoustic power. Okay, so you want higher Q factor, you're going to have lower efficiency. Okay, you want higher efficiency, you'll have to contend with lower Q factor. Okay, so what people do is they try to go higher in the carrier frequency, in the center frequency. But for underwater acoustics, the problem is you can't keep going higher and higher in frequency, because as I said, the usable bandwidth goes only up to higher few hundred kilohertz. Okay, so that turns out to be the problem, and why we cannot push as many bits as we would like in a, say, a high-speed internet communication link. Okay. Now the other challenges, I showed you what it was for the deep water channel, right? Multipath can be a problem if, depending on the kind of ocean depth that you want your communication link in. Okay, in shallow waters, right? So if you have few tens of meters, or even just 100 meters or less than that, right? So what happens is sound is going to hit the surface, it's going to hit the bottom, lose energy, right? It's going to come back up, then lose energy, right? Maybe make its way back up and then lose energy even further, right? So interactions with boundaries are an issue. Okay, so that, as communication engineers know, that's going to cause multipath, and also that is going to take energy out of the signal. Okay, and then there's other issue, which is if you're looking at long ranges of communication, there is also the effect of oceanographic fluctuations. Say you want to use the deep water sound channel for sending a signal far using the ocean acoustic waveguide, as I showed, right? But the problem is there are issues like internal wave fluctuations, okay, which make the ocean acoustic medium a random medium, and because of that there is signal fluctuations. Okay, so those also cause problems. Okay, but now, so then if we cannot use it for high speed internet, so what is underwater communications good for? Okay, now as I said, sound can travel to far ranges, but you have low bandwidth, right? So you could use it, right, to maybe turn on, turn off a switch or a device at pretty long ranges, at ranges hundreds of kilometers. Okay, not to really transmit video over hundreds of kilometers of ranges, but maybe turn on, turn off switch. Maybe you want to monitor a certain device that's sitting somewhere at some location that you care about most, then that's good. Or maybe a submarine wants to send some distress call, some SOS, then it can do that, right? You don't really need high speed internet for that. So use the properties of the waveguide for that. Okay. The other one is you have to use high speed, but over small ranges. You want to monitor some installation, you can't go there, right? So you're sending a bunch of AUVs to monitor some critical installations that you have. Okay, but maybe you have a node sitting somewhere close to the swarm of AUVs, and the AUVs are taking pictures, the AUVs are taking videos and sending it. Okay, so then you don't have to send divers, you could send AUVs there, and you could use communication link but over shorter ranges. Okay, so it is for such kind of applications, okay, that you use underwater acoustic communications for, right? Okay, thank you.